Okay, so I have completed the, the homework assignment that I gave for the WKB chapter 8, and I think there are still some things about the content in this chapter that I would like to touch on to help you to complete the homework and to get a better grasp of what you're doing as you do it. I think it's always possible to read the book, follow the examples, and somehow muddle through. But I think it's particularly here for this WKB where the technical job of completing the calculations is a task in itself, that I don't want that to obscure the elegant simplicity and naturalness of the WKB method as a method of approximating the full Schrodinger equation solutions. So we said earlier that because of certain weaknesses, WKB fails as a substitute quantum mechanics, but it can work in appropriate places, locations in space as an approximate solution to the complete Schrodinger equation uh, wave function. And in particular, we want to stay away from the vicinity of a classical turning point, but it can work either on the classically allowed side where the solutions are oscillating, or as we saw at the end of the last lecture, they also work on uh, the other side where it's classically forbidden, in which case you replace the WKBe, the I phi, with e to the plus or minus phi alone, where that phi has been calculated, where it's an integral of p, except that the p is now the imaginary substitute for p, where the square root, e minus v, has been replaced with the positive number square root of v minus e. And that's what I'm depicting here. So if we had a potential that had arbitrary wiggles in it, but was below the energy, and here what I'm trying to depict by this dashed line is the energy at which we're interested in computing the wave function, eigenstate of h. Uh, Here we see in this classically allowed region that v is less than e, and therefore we do have a positive kinetic energy contribution. That's classically allowed. However, at some point you see the wave function, the potential passing through the energy, and then classically you would say this is a turning point and that these values of x beyond x naught would be disallowed. But quantum mechanically, through tunneling, they are allowed, and so as long as the potential doesn't go too high above the energy, you should get an appreciable probability of finding the particle in that region in space. So the oscillating solutions on the left side in this example have the classic WKB form, 1 over the square root of p, where that p really just measures the depth from the energy all the way down to the ocean floor here, which is the v at that point in x. And if we take the square root and reciprocal of it, that's the amplitude of the WKB wavelet here, and then its phase, e to the I, can be either plus or minus phi, where it's the same number phi, just taken with a different sign of this imaginary factor. That covers this region here, but not too close to the dashed line, the keep-out zone. On the other side, the corresponding damping or exponentially rising WKB solution has this 1 over square root of p amplitude in it, just as the other side did, but now our exponential phase factor has become an exponentially damping or rising factor, which I've tried to represent here by a wave function that has this exponentially rising behavior or the exponentially damped behavior. That's WKB in a nutshell. Okay, both regions have this classic shape. The only thing we have to remember is which square root we take when we are computing p here, and whether or not we include the I factor here, depending on whether we actually took a negative inside the square root and absorbed the I, that would be in the classically forbidden region, or whether we just computed the square root straight off and left the I outside, that would be in the classically allowed region. Now here, we're confronted with a problem. We have solutions on the left and right, but in quantum mechanics, we don't know what the overall global solution is until we know the rules for matching them at the boundaries where they touch. Now, in ordinary Schrodinger quantum mechanics, that was just a part of solving the differential equation, where we realized, being a second-order differential equation, to be well behaved, it had better have smooth and continuous first derivatives, or the second derivative is going to be sick. The first and zeroth derivatives have to be continuous at the places where you join, and those become the algebraic solutions for obtaining the coefficients A, B, C, D, etc. This is the familiar procedure for joining stepwise potential solutions. Here in WKB, we have disjoint regions over which we're able to write down WKB solutions, but matching them up across the two boundaries is a challenge. That's what I've tried to represent here. Now I've drawn again the same kind of rough and crude potential to the left, classically allowed, to the right, classically forbidden. Now in the crossover zone, we have this keep out region where WKB has no clue what to do. On the other hand, if I imagine WKB approaching in its validity to the sort of this gray zone here to the left, and on the other side from the classically forbidden region, a gray zone to the right, then it's a rather restricted region over which we're faced with the conundrum. And what I've tried to draw here is, imagine that perhaps it's narrow enough that we could approximate it by a straight line that crosses through 0 at x0. Maybe we can actually treat this crossover region by solving not WKB, which is hopeless here, but first principles Schrodinger equation. But now we're going to use a simplified picture where it's not the full V we're interested in, but just this restricted V, where V is a straight line, linear potential. We know the V straight line potential when it's horizontal. We also know how to solve the second order equation. It's interesting, isn't it, that we've come so far in quantum mechanics and we haven't solved the constant force problem. Imagine spending, 2 semesters and getting in classical mechanics, getting to finally to the constant force problem in ordinary classical mechanics. Well, in quantum mechanics, it turns out that the constant force problem is kind of pathological. It's because we always like to deal with Hamiltonians that have a minimum. Notice this Hamiltonian, if I considered this potential as going all the way up here and all the way down here, it would have no minimum, because the particle obviously could slide here forever and ever going downhill. And we're not used to trying to deal with Hamiltonians that don't have a minimum energy, don't have a ground state. But it turns out that one can nevertheless attack it by just using the solutions to differential equations, and we get actually surprisingly normalizable states in such a situation. Weird, but true. That'll be our next job. Let's construct what lives in this space. Okay, here's the potential. V equals AX. Let's now solve that potential. Here's this full Schrodinger equation using V equals AX. Now I'm just going to convert it into a simpler form by moving everything except the derivative term to the other side, factoring something out, and defining explicitly the classical turning point at x naught, which is where the potential plus the total energy equals 0. And of course, x naught is nothing more than E over A. With that substitution, we can now do our rescaling. So we're going to define a rescaled dimensionless length, which is going to be a substitute for x. First thing we're going to do is we're going to make that z 0 at the classic turning point, so we shift our origin. Second thing, we're going to multiply it by something which has the dimensions of 1 over length to try to simplify and put the differential equation in the most familiar form possible. So here you can see that when I used the chain rule, second derivative of psi with respect to x is the second derivative of psi with respect to z times the second derivative of z with respect to x. That gives me 2 powers of alpha. I'll bring those 2 powers of alpha underneath over here. Then I'll also multiply and divide by alpha, so I have an alpha here, which is going to eat this x and minus x naught and become z. And that gives me an overall alpha cubed. And here's the z. Now notice, I haven't said what alpha is. Let's make this alpha cubed, just cancel this term. Then this whole thing becomes 1. And this is my value for alpha that gives me this simple, super simple looking differential equation. Second derivative with respect to x squared is equal to x times the solution. Homogeneous. It's a very simple differential equation. It's been worked out long ago by Airy. And these two classic solutions is second order. There are two independent solutions. And they have all the nice behaviors you'd expect for wave functions for such a potential. First, what do we expect? Oscillatory on the left-hand side. Notice this is the classical turning point now at z equals 0. Exponentially behaving on the right side. Second, two solutions. One of them exponentially dying on the right side, the other one exponentially rising on the right side. Second thing we see. Notice how nice and smooth they are across the classical turning point. Nothing wild. That's because Schrodinger behaves like that. Solutions to the Schrodinger's equation do not contain divergences or singularities just because you pass through a classical turning point. So armed with these two solutions, we're able to construct any general wave function that is an eigenstate of the Hamiltonian with a potential that has the form AX. Now, we're going to be interested especially in using these functions to connect to WKB out over here and to WKB out over here. And for that purpose, we're not interested simply in the detailed form everywhere, but in what does the shape out here, far from z in the negative direction, and out here, far from z equals 0, in the positive direction. And here are the two forms written down. These you just simply have to take from, say, a standard formula book, because the Airy functions are well tabulated and understood and known, but they're not intuitive. You would necessarily be able to read them off intuitively without doing a long proof. Here they are in the oscillatory side, which is negative z. Notice that they have this 1 over z to the fourth times a sine of something that depends on z. This is not exactly z, but it's a simple function of z. We'll see in a minute that it's a polynomial. And here's an additional phase that gets the zeros in the correct positions on the left-hand side. The only difference between those which join on the other side to the exponentially damping, that's the AIs, and the exponentially rising ones, is that this is a sine wave and this is a cos wave. So they're just shifted in phase. That's it. All right, now let's look at the other side. As expected, one of the two behaviors goes exponentially falling and the other one exponentially rising. And we haven't specified what the theta is. I just want you to know that this theta is monotonically increasing with z. Notice that in this case, we are sampling the function theta at positive z. Here, we were always sampling it at negative z. And that's something to keep in mind, that you'll actually be, to compute Airy function values, you'll always be taking z's that are positive. In this case, your z is negative, so you make it a minus z to bring this thing positive. So we'll only be sampling the theta function at positive arguments. Now, just one more thing I would highlight. There's one odd feature that always stands out and is a gotcha, unless you notice it here. Notice that these denominators all look the same. 1 over absolute value of z to the 1/4, the square root of pi. Look at this too. Just don't forget that the exponentially damped one, out of all four, has a 1/2 in it relative to all the other coefficients. The a's are exponentially dropping and the b's exponentially rising. If you want to make your wave function to be normalizable, you'll want to choose one or the other. Okay, now proceeding on, what is this function theta? Well, if you look it up, you can see that the function theta is just a polynomial, it's just z to the 3/2. If I sample at minus z, then I put minus z first, then I raise it to the 3/2. That result gets multiplied by 2/3. With this substitution in these appropriate places, these solutions can be easily verified to obey the Airy differential equation that I mentioned above. Now let's look at them for a moment. Other than having the proper oscillation behavior on one side and exponential behavior on the other, they also have this eerie resemblance to the WKB solutions. Notice that they look like something like 1 over the square root of something here, and e to the plus and minus something here on the oscillatory side, 1 over the square root of something, and e to the plus and minus something without an I on the exponential side. Could this really just be a clone, once properly interpreted, of the WKB solution? And so we'll see that that in fact is. To show that, instead of asking what theta is, which is this simple z to the 1/3, and then z can be replaced with x, it's just alpha x minus x naught, which gets raised to the 3/2. Let's compute instead the WKB phase. If we were doing WKB instead of Airy, what would we have put in those exponentials? We simply compute P integrated over x, and here's the integral. Notice what I'm going to do here first. Let's consider the x greater than x naught, so this is starting at the classical point and pressing forward into the classically forbidden region in the positive x direction. And because of that, what's under the radical, is actually a negative number. I convert it to a positive number by pulling out an I. And I haven't committed on the sign of the I, but now I'm allowed to write what's inside the radical as a positive value. This turns out to just simply be the square root of x minus 1 dx, that integral. You can look it up. It has, or you can even just do it analytically, it has the value of 2/3. The argument, whatever you had inside there, is raised to the 3/2. To test that, you can just take the derivative of it. Take the derivative with respect to x, brings down 3/2, that kills off the 2/3, and leaves you with x minus x naught to the 1/2. All good. The factor 1 over the square root of x naught is simply coming from factoring out this denominator. All right. Now, let's put together all the pieces. Let's substitute in for x naught in terms of its values in terms of a and m. When I do that, I combine it with this square root of 2me, I get this factor. Lo and behold, what is that? That is nothing more than alpha cubed square root inside the square root. Or we can simply write that as alpha to the 3/2. It turns out that alpha inside the power 3/2 times x minus x naught has another name. It's called z. And so that whole factor there, everything except the 2/3, is z to the 3/2. So what is this WKB phase? It is 2/3 z to the 3/2 with a factor I pulled out. And notice 2/3 z to the 3/2. So this theta of z that was so ubiquitous when we were looking at Airy functions is nothing more than the integral of p, known as WKB phi. Okay, and that we've proved that that was true in the regime where you're classically forbidden, where x is greater than x naught. Let's consider the other side. Here, let me just put it down for a record that on that side, the WKB damping factor phi, WKB, is nothing more than theta of z. On the other side, this is the oscillating classically allowed side. The WKB phase is obtained by integrating backwards from the classical turning point backwards. So this is a negative going integral, slightly maybe a little confusing, but with a minus sign you could turn it around and make it plus x. This would be x to x naught. Anyway, we don't have any problem with a negative radical this time. Everything's well behaved because it's classically allowed. It's a straightforward integral. What do we get? Other than the negative needed to rearrange the positive ordering of the two limits, we end up with 2/3 times z to the 3/2. Just keep in mind that because this is x naught minus x, that's actually minus z. Turning that number, which is a negative number, you can imagine, x naught minus x, and, well, no, x naught minus x is positive, but in this region z is negative, so turning z into a positive number requires putting a negative in front of it. So negative z is a positive number. That makes it easy to take the square root without asking which root of -1 you're taking, because it's not applicable. And this turns out just to be negative theta of negative z. Okay? And so what we had in the Airy function on the oscillating side, sine of theta of negative z plus pi over 4. That's what the Airy function limiting value is for negative z. What is that? Well, what is a sine? It's e to the I its argument minus e to the minus I its argument times some factor. And what is the cosine of that? It's nothing more than e to the I theta plus e to the minus I theta. And of course we can't forget the pi over 4, but it just comes out. If I think about what happens if I put it up here, I can just factor it out as a constant factor. E to the plus or minus I pi over 4 is something like 1 plus I, or 1 minus I, over the square root of 2. So this is just a constant phase factor, part of the coefficient of the oscillatory piece. This is the oscillatory solution. So this Airy function maps straight onto the WKBs. Okay? So in fact, the Airy functions continue straight into the WKBs. And this gives us guidance about how to use the Airy function to connect the WKB on the classically allowed side with the WKB on the classically forbidden side. And there are two viewpoints that I'd like to stress. The first one would be that we can sort of stick with the Airy function and say it's really the Schrodinger solution to this linearly sloping potential that has in it all the ingredients that we need to exploit WKB on everywhere in space. And that's going to be my anchor. So what I'm going to do, I'm going to imagine that my whole potential has been replaced with a linearly sloping one. And then what I'm going to do is I'm going to kind of think of it like an elastic, stretchy x-axis. And where the potential gets deep, I'm going to stretch it. And where the potential gets shallow, I'm going to shrink it to try to collapse and shrink it, the x-axis, kind of like changing the metric, in order to get the potential to distort from the straight line. And by doing that, I kind of do a geometric transformation, a continuous geometric transformation from the linearly sloping Schrodinger problem to an arbitrary potential that is on the left-hand side negative and on the right-hand side positive with respect to E. And with that prescription, what I'm saying is that my Schrodinger solution is the Airy function where I replace theta being trivially z to the 2/3. Remember that thing? That 2/3 z to the 3/2, sorry, with the actual WKB phase. So that's all I'm going to suggest that you do. You take the Airy solution, you just write it down, but then you reinterpret the theta of z, not as simply z to the 3/2 times 2/3, but replace it with a WKB phase that contains the actual facts about the dependence of V on X away from the classical turning point. And that is certainly valid, and it exploits the fact that the Airy function continues into a WKB shape. But another viewpoint which emphasizes the role of the area function not to actually substitute for WKB as a full solution to the problem, but just to stitch together the two pieces. Let's let WKB solutions stand on their own on either side of the turning point, and then I really meant area, let the area functions here guide how you connect the coefficients from the left and right going oscillators on the left-hand side to the left and right going exponential dampers on the right-hand side. Okay, and this one little map here I think will be super useful as you work on the homework. Here on the left-hand side, you can see WKB oscillators. And maybe I can take just a moment right now to insist that left and right are not absolute. What if your potential is falling? Then you just exchange it. Your classically forbidden region would then be on the left-hand side, and your classically allowed oscillating side would be on the right-hand side, and it's completely interchangeable. And of course, you would have to replace your z with minus z everywhere. And all of the orderings of the integrals would reverse. But nothing about this whole treatment is changed in the least. So going back again to the convention where left-hand side is oscillatory, the WKB oscillatory solutions look like e to the plus I phi. There's the WKB phase. E to the minus I phi. Which combination of the two? Well, that depends on how the matching works, because we're going to have to continue and match it to the other side. What does the WKB look like on the other side? It can be a falling function, or it can be a rising function. Which one? Aha. This is usually the telling point. If you are dealing with a bound state, you must choose one or the other, not both. Over here, generally you end up with both, some superposition. Over here, generally, if you want to have a normalizable state, you're going to have to throw away one of these two, because the other one, keeping them both, will most certainly ruin your ability to normalize the state. As you go out to n equals infinity, you're going to want these two you're going to want whichever one of these functions pushes the integral to zero, okay, or pushes the contribution to the integral out at infinity down to zero to make the integral convergent. So if you're working on the right-hand side, this is the term you want to go to zero. If, on the other hand, you're working with the left-hand side out, where you're looking at a wave function as x goes to minus infinity, then you want the damping solution, which is this one. Okay, choose whichever one you want. That's going to guide everything else. Now, area is going to tell you how. Let's imagine that this is the one we chose. This coefficient's non-zero, okay? Then that connects to the area function, which has that particular solution. That one we called AI. Remember, this was the BI down here. This is the AI, the one that had the minus e to the I phi in it. And don't forget the 2. So these two have to connect. Notice the shapes are the same. Therefore, these two, this one here being non-zero means this one's non-zero. This one being 0, of course, means this one's 0. So that means that if this area function is selected, then when you reach over across the classical turning point, the oscillatory shape has to have this form, sine of sine of theta of z, and this would be theta of minus z, which I evaluated above, and you can look back above, you can see that it's minus phi. And there's the plus pi over 4 of the area function limiting asymptotic form. What is the sign of minus phi? Well, it's a particular superposition of e to the plus I phi and e to the minus I phi. And which one it is, of course, you all know how to do. You do it by remembering that the sign is e to the plus I phi minus e to the minus I phi over 2i. You then fold in the extra phases that come from including the e to the I pi over 4 and the e to the minus I pi over 4. And last but not least, you do not forget the minus sign, which exchanges the e to the minus I phi coefficient and the e to the plus I phi with each other. If it turns out that you're working on the opposite side, You're trying to control the wave function as x goes to minus infinity, and you select this particular term. The same thing applies, except you're going to have a cosine. And so the particular superposition of these two WKB terms that you're going to need to match to this one on the other side is governed by how the cosine sticks together, this one and this one. Don't forget the pi over 4, and don't forget the minus sign. Okay, I think that this little map here tells you everything you need to know how to do WKB matching for bound states, and it'll be useful for you in working through the homework problems. That's all I had, and good luck on that homework. It did take me 12 pages, so leave yourself adequate time, and I'll see you on next Wednesday. So long.